Now, graphs here is going to be somewhat of a long lecture, so I don't expect that we're going to be completing this entire thing today. So we'll reach up to a certain point and then we'll stop regarding our graphs lecture, and then in Wednesday's session we'll complete the lecture as a result. So the material for trees will be covered coming down to your third quiz, not your second quiz. So your second quiz should be up to, let me just give you a good indicator. Let's see. Although I will give you a forum post regarding this, but I'm telling you guys in a little bit in advance. Your second quiz should be up to either the end of sorting and searching or up to the end of linked list. But I will give you definite confirmation of that once I start writing the forum post regarding this with the second quiz. What I can tell you is that your second quiz will be, once you get the announcement, you will have like ample time to know how to go about preparing for it and whatnot. I believe either the second quiz will be either on this weekend or it will be sometime next week. But like I said, once I put up the forum post with all the details, you will get confirmation regarding this. Yes, it is possible for a try that you can have many null nodes for trying to figure out what word is going to fill in as a result. You saw that in particular when we had all those star nodes in illustration representing the end of a word or basically a sort of null as a regardless of how you went about traversing it. Alright. So like I said, graphs here is a particularly long lecture, and like I said, I don't expect us to complete this in today's session. So we'll stop at a comfortable point and then we'll complete graphs in Wednesday's session and finish that topic in particular. Yes, you will be able to see your quiz 1 feedback before the second one. I did ask this at the start of today's session if you were able to see the feedback, and people responded that they weren't able to. So it's just a matter of changing one of the settings in the quiz so that you'll be able to see your feedback. And I will do that once we finish today's session. Alright, so we start with graphs now. And basically graphs are just a fancified version of trees. So once you understand your tree theory, understanding graph theory here is going to be somewhat similar to what you have. But whereas trees could not have cycles, graphs actually can have cycles. So that's why we have the statement that not all graphs here are going to be trees. So a tree is basically a connected graph without cycles, but a graph actually can have cycles within itself. Mathematically, mathematically, graphs are defined by an expression known as V, E, where V will be your nodes referred to as vertices, and E will be the connections between the nodes referred to as edges. Now, I did provide a lab resource for graphs online, and that's going to actually help you guys a little bit more with regards to how the code operates with graphs and so forth. This lecture here is actually giving you guys the physical explanations and the illustrations as to how certain things will operate with regards to the code that you see in that additional document. So if we watch an example graph here, a vertex will be our node, where we have 3 letters for each one of the airport codes here in our physical example. An edge will represent a connection between nodes. And the edge here basically has a weight. This weight here would be our mileage of the route between 2 particular airports. And we can have multiple different connections between nodes, as we can basically see here, by any sort of graph that we're dealing with. Graphs can have directed or undirected edges, meaning that If it's a directed edge, there's only one way for data to travel. And if it's an undirected edge, data can travel both ways between nodes. It's also possible that where we had, for trees, we had subtrees. Graphs also can consist of subgraphs. And such that once we have any pathway between every pair of vertices, we refer to this as a connected graph. It is possible for us to have isolated sections of graphs where we don't have any pathways, and this is also referred to as a disconnected graph. Graphs differ from trees because it's possible to have cycles where you can loop back to a particular node. An acyclic graph has no cycles and is basically a type of tree that you also can encounter. But remember, graphs differ from trees because they actually can contain cycles. So we're going to move on to a little bit of terminology regarding our graphs as such. So the end vertices here are going to refer to as two vertices or two nodes that are connected by an edge. So for example, the end vertices of edge A would be and B. Edges incident on a vertex refers to which edges are connected to a vertex or which edges are connected to a particular node. So node U here has edges A and C connected to them. Similarly, node V here has edges A, D, and B here connected to it or incident to it. Adjacent vertices are what we refer to as vertices that are neighbors. So basically vertices that are connected to each other. So vertices here being nodes will be that U and V are neighbors because of the existing connection here, represented by edge A. And U and W here are also neighbors because they have an existing connection represented by edge. The degree of a vertex or a degree of a node refers to the number of connections that a vertex or node has. So for example, vertex V here or node V has 3 connections, A, D, and B. So the degree of vertex V would be 3. Parallel edges is when we have multiple edges that are connected to a pair of vertices. So if we have multiple connections between 2 nodes, these edges here, because they don't intersect with each other, but they basically connect between these 2 nodes here, are parallel in nature. So H and I here are parallel with respect to vertices X and Z. A self loop is basically when you have an edge that loops back to a particular node. But an edge J here, because it loops back to vertex Z or node Z, is a self loop because it just loops back accordingly throughout the entire. A path refers to as a sequence of alternating vertices and edges where we have a start vertex and an end vertex. So for instance, if we wanted the path between U to Z, this can be U, A, V, B, X, H, Z. It can also be U, A, V, B, X, I, Z. And then to make things a little more complex, we can go U, C, W, E, X, I, Z, and so forth. Listen all the possible paths that are required for any connection between U and Z. But any path is basically okay. We're going to see later on why certain paths are going to be better than others, in particular what we're going to be encountering a shortest path algorithm. And we'll see how that operates later on, probably not today, probably in Wednesday's lecture when we continue our material here. And we'll see why this is important. A simple path is where all the vertices and edges are going to be distinct. So no vertex or no edge is going to repeat itself. So that means like we won't go, for instance, if we're trying to get to Y, we won't go U, A, V, E, X, E, W, F, Y. That's all distinct. But it's not like to say like if we're trying to get to another node here in particular, we're not going to be repeating the node. So we want like UAV X8ZI XGI X repeats here. So that's not a simple pass. So all vertices and edges must be distinct for a simple pass. We don't have any repeats. A cycle is where we have a circular sequence of alternating vertices and edges. So a cycle basically represents any sort of loop that we can form within our graph. So if we try to loop back to U here, we go U, A, B, D, W, C, U. That's going to be a cycle. Similarly, we can have U, A, V, B, X, W, C, U. That's also another cycle, and we keep on going on. Similarly, with the simple path, the simple cycle will be where all the edges and vertices are going to be distinct in nature as a result, and we have no self-contained loops throughout the entire thing. All right. So before I go on to anything else regarding graphs, are we clear on the terminology used here for each one of these in our explanations? If there's something you don't understand regarding any one of these terminologies, feel free to ask now. Sure. So a cycle basically means that your start point is also going to be your end point. So, for example, we can have U, A, V, D, W, C, U. And we can also have U, A, V, B, X, E, W, C, U. For a simple cycle, we don't have any repeat nodes or any repeat vertices other than your start point. So for example, we can't go U, A, V, A, U. We can't do that. That's not going to be a simple cycle because it comes like with a repeated A twice. I'm not too sure if it's the same as a Hamiltonian cycle, but I will make a note to check on that. Just down here. Cycle. I'll check that for you, and I'll put a forum post regarding this. So yeah, cycles are basically how you can go back to a particular node. A simple cycle would be that you have distinct vertices and edges except for your start point regardless. So UAVAU will not be a simple cycle because edge A here repeats itself. But if you go UAVDWCU, this is a simple cycle because you have your start point and your end point here being, and no point in between the start and the end point repeats itself. So no edge and no vertex repeats itself. Right, any further questions on the terminology? Alright, doesn't seem like we have any further questions regarding this. Okay, let's go on. Now, the most common way to represent your graph, being your list of vertices and edges, is to use something we refer to as an adjacency list. And basically, this list here represents a nice ordered way actually to represent the connection between your vertices and your edges. So we can use a simple class definition here for using an adjacency list, where we have our same node structure here represents for our vertex, and the graph structure here representing the links between the vertices being our edges. So we need to use the graph class here, and it's in particular the reason why we're using that graph class is because it's not necessarily that you can reach all the nodes from a single node. You don't need additional classes to represent a graph. You can use either an array or a hash table of lists, or even a simple vector in our implementation here that represents this adjacency list as a result. And the example code for adding the edges here is actually given using that vector class, which is a standard library in C++, to actually store each one of these edges between two particular nodes. Now, all of these code here that you're seeing, like I said, is provided in that lab handouts or that lab additional resource underneath this lecture. So I do encourage you guys to go and look at that and try it out and watch it back when we are reviewing this lecture, see how the adjacency list works as a result. It's also possible, instead of using an adjacency list, you can also use an adjacency matrix, where you can indicate an edge from node I to node J, and you actually can have a weight within the matrix indicating what's going to be that weighted of that edge. One thing to note though is that for undirected graph, your adjacency matrix will be symmetric, but for a directed graph, it not necessarily is going to be symmetric. So I'm going to give you an example here of how this actually works, is that you list out all the nodes here in order of their particular values as the row and the column of this adjacency matrix. And then for each possible edge between the two, you look for the intersections within the matrix to see if that edge actually exists. So like, for instance, 0 and 0, there's no edge in between that, so that's going to be 0. But in between 0 and 1 here, we do actually have an edge. So we represent this as 1 here, indicating yes, an edge actually does exist. Between 0 and 2 here, if 0 is our start node and 2 is our end node, an edge does not exist. So I'm just going to illustrate this on our matrix. So these here will be start nodes. These here will be end nodes. So the reason why this here is 0 is because we're watching from 0 here to 2, and that connection does not exist. So that's why we get a value of 0 there as a result. Similarly, between 0 and 3, there's no connection whatsoever, so we just put a 0 here. However, if we watch our starter node here being 2, and our end node here being 0, there is a connection. That's why we put a 1 here to represent. So these 1s here represent where edges exist between vertices, and the direction of the edges are also important by listing which part of the matrix here are going to be start, part is going to be end in regards to our nodes or vertices. It's also possible, instead of this being 1s and 0s, the 0s can represent no edges or no connections, and instead of having 1s here, we can actually have the physical weighting of each one of these edges. But it's also particularly important that we pay attention to if these values here for our vertices represents the start, or if these values here represents the start instead. Because either this row here or this column here, you need to specify if it's going to start and which one's going to be end in order to have your order within your adjacency matrix. Alright. Any particular questions regarding the adjacency list or the adjacency matrix? Feel free to ask now. Yeah, sure. So, in making our adjacency matrix, we watch each one of these vertices here, where a vertex is a node. The edges are the arrows, yes. So, we list out all the nodes here as our start row here for our adjacency matrix, and our start column here as well for our adjacency matrix. We need to specify either if this part here is going to be the starting nodes, and if this part is going to be the end nodes, or if we flip them accordingly. So for this particular example, we use the starting column here with our list of vertices or list of nodes here to be, okay, this is where we start from, and our starting row here in our adjacency matrix to represent these are the nodes that we want to be ending at. So 0 to 0, there's no connection, so that's why we have a 0. 0 to 1, there is a connection, so that's why you have a 1 here. 0 to 2, there's no direction connection here. So we have no connection going from 0 to 2, so that's why we have a 0 here. And similarly, 0 to 3, there's no connection between that, so that's why there's a 0. Now, let's watch this in the reverse order where we have a connection from 2 to 0. So we start at node 2 here, and then we end at node 0. And because there's a directional connection here, that's why we have this 1 in this particular case. There's no directional connection from 0 to 2. So that's why we have a 0 here. The edges here are the arrows, but in this example graph. The vertices here are the nodes. It's also possible that if each one of these edges here had a weight, and if there was some numerical value associated with them, instead of storing these as 1s, we can actually put those numerical values in. In instances where there's no physical connection or no directional connection we just leave the zeros as is in our adjacency matrix. So the adjacency matrix is just a really fancy way of us simply stating what physical connections are possible between our vertices in our example graph, where these physical connections are the edges that connect each vertex to one another. Nice. Any further questions? Alright, doesn't seem like we have any further questions. So, depending on how you implement your graph, you can use the adjacency list or the adjacency matrix. A lot more people prefer the adjacency matrix because it's a lot easier to work with. But it really depends on your style and how you intend to implement your graphs. In some cases, you may end up encountering somebody who actually did implement it with an adjacency list. So it's a little bit important that you understand how each one of these operates, even though the adjacency matrix is a lot easier to understand than the adjacency list. Alright, so there are two common ways for us to actually go about searching a graph, and there's going to be referred to as breadth first search or BFS, and depth first search, which is also DFS. We're going to be looking at each one of these in turn because it's required that we know how each one of these search algorithms work. So for breadth first search or BFS, we start at the root or any other node that we select to be our root, and we explore each neighbor before we go on to any of their children. As such, we go wide first before we go depth. So it comes like if we start at 0 here, we go 5 and then 1, and once we exhaust, and then 4, and once we exhaust all those, we then move on to 1, 4, and 5, and then we do a search there accordingly for each one of these connections, and we keep on going as such. So we do a wide first search, exhaust all the wides, and then we go on to the next depth or the next level, and then we do that search at that level, wide again, and we go on to the next level and we keep on going and repeat it. So for example graph here, we're going to see how this actually operates step by step. The assumption for BFS is that you may think it uses a recursive technique. And this actually is quite wrong. It doesn't use a recursive technique. It actually uses a queue structure that we saw in our previous lectures last week. So anytime when you're implementing breadth first search, always use that queue. Do not use a recursive method. Use that queue, because that queue is going to make your implementation a lot simpler and easier, and a lot easier to track what you're doing regarding breadth first search. Depth first search. Sorry, right. So I was giving my explanation here regarding breadth first search. So breadth first search is that we start at node 0 here, and then we go node 1, node 4, and node 5. And we exhaust all our links here for node 0 as a result. We then go on to our next possible level that can actually exist. So we see 5 doesn't really have any connection, so we ignore 5. We then go 1 and 4, so we then have to see what physical connections actually do exist. So from 1 here, see that we go to 3, and then we can go 2, and then we can go 4 as a result. But we already visited 4, so we don't need to go back to that. So that's how we go about doing breadth first search. So the order in which these nodes are visited represents the order in which you go about doing breadth first search. Depth first search is where you go deep first, and then you go wide. So you also start at the root node or any node that you select as a root, and you explore each branch completely before you move on to the next possible branch. So a good example of this is that, okay, let's say we start at node 0. We go at node 1, and then we explore how deep this actually can go. So node 1 can go to node 3, and then to node 2, and then node 3 here can also go to node 4. And we've explored all of these nodes here already. So the next node from 0 here is that we just need to explore 5. And we basically finish depth first search as a result. So it operates in, I won't say the reverse order of breadth first search, it's just that the order is different, such that depth first search goes deep, then wide, breadth first search goes wide, then deep. You already seen an example of depth first search here in our tree code, which actually is a pre-order traversal. Your post-order traversal and your in-order traversals are actually forms of depth first search. So that example code that you saw in your trees lecture can actually be applied here to your graphs to do depth first search. Now, there's one key difference here for graph usage. You need to make sure that you check if the node has already been visited to prevent any revisits. And it's also possible that if you don't do this check and you keep on revisiting the node, you'll end up getting stuck in an infinite loop and you never complete that first search. So that's why it is impossible. That's why it is important to have this node tracker to keep track of it, so that way you don't revisit any nodes that you already have visited when you do in-depth first search. Now, each one of these search algorithms are used for different scenarios. The more popular one is going to be depth first search, because that's used to visit every node in the graph if you need to do a very exhaustive search. But if you need a very fast search, in particular if you're trying to find the shortest path between two nodes, you're going to have to end up using breadth first search. So a good idea would be is that you have your graph code and your additional resource. But even if you don't want to use the graph code, try using breadth first search and depth first search on your example graphs in the previous slides, and see how you'll find your path between node 0 and node 3. And you want to see how it differs quite greatly in trying to find these paths. Alright, so before I move on to the other subtopic that we have here, are there any particular questions on breadth first search and depth first search? Feel free to ask them now. Here. Right, yeah, sure. So breadth first search is where you go wide first instead of deep. So it's like we're at node 0 here being our root, and we want to explore what are all available connections from node 0 for first possible level connection. So it's like we're at 0, and then we want to see, okay, for our first link between 0 to any possible node or any possible vertex, let's see how many first links that we actually can have. So we go from 0 to 1, okay, that's a depth of 1, 0 to 4, which is a depth of 1, and then 0 to 5. So once we explored all available links of a depth of 1 from node 0, we then move on to the next depth, being that we will be at 1, 4, and 5 here. And we need to explore nodes that are connected to these at the next available depth required. So let's think about it this way. If I redraw my graph to show this, this is actually how it would be. So it's like if we're at node 0 here, and we have 1, 4, and 5. And this here will be level 0, this here will be level 1. So we already visited 1, 4, and 5 here. So 5 here doesn't go anywhere, so we don't need to do any more searching here. That ends here. 4, if we're at 4, 4 doesn't have any outgoing edges, so we basically stop here as well. 1 here, we need to check what's going to be our outgoing edges. So 1 here connects to 3. And then, okay, does 1 have any more outgoing edges? Yes, 1 connects to 4, but we already connected that and we checked it back. So we don't need to bother with this connection because we already visited node 4. And then, okay, we are finished with that. So we just check for 3. 3 connects to 2. And 3 also connects back to 4. But we already visited node 4, so we don't need to bother with this as well. And because we visited all nodes here as a result, our breadth first search here finishes at that point. So it comes like if we just redraw the graph to illustrate how we go about visiting each one of these levels. So it'll be level 2 here, and then level 3. So in redrawing the graph, we see that we visit the nodes at a particular level, being the width here or y, before we go to the next particular level, which is going to be our depth. And any nodes that we have already visited, we don't need to revisit that. So we just ignore those links because we already visited those nodes, and then we just focus on the other possible links between nodes we didn't visit as yet. And that's how breadth first search actually works. Right. Any more particular questions on BFS and DFS? Alright, so it doesn't look like we have any further questions regarding that. And the next topic that we're dealing with regards to graphs is topological sorting, but I'm watching the time here and we're not going to complete that in time. So we'll stop at this point here for today. And in Wednesday's lecture, we'll continue from here and hopefully we'll complete graphs on Wednesday. Meaning that next week, Monday, will actually be our last lecture, which is going to be bit manipulation. And after that, anything else from that point will be tutorials or any sort of sessions that we need for any sort of practice and so forth. It's free to request those once we complete all the material, regardless, in particular. We can also use those sessions as well for any preparations, or any misconceptions that you guys have, any trouble that you also have as well. So we can address those in particular, but like I said, those sessions are going to be requested sessions. And it's helpful that if you want to request these sessions, that you come in advance regarding this with the topics that you want to talk about beforehand, or any particular things that you also need some sort of clarification on. That's free as well to ask about regarding these things. Wednesday class is not going to be a 2-hour class, it's going to be a 1-hour class. That's going to be from 1 to 2. And I believe from 2 to 3, you'll be going on into the BBC classroom with Dr. Paransing. Alright, so like I said, Wednesday class is going to be 1 to 2. We'll be continuing here from topological sorting, and hopefully we will finish off graphs on Wednesday. If not, we'll go on into on next week Monday, and then we will be doing the last lecture on next week Monday as well, which is going to be bit manipulation, sorry. And once we complete all our covered material, any other further sessions will just be practice, or any misconceptions that we need to clear up regarding anything in particular. Alright, so if there are any further questions regarding the material of today's lecture, feel free to leave them down in the comments below, or you can write me accordingly and I'll respond to you guys enough as well. I will make sure that I check up on that quiz and that Hamiltonian question that was asked in the lecture, as well as any other matters that came up as well. I will address them as well over the next few days or within the next few hours. But until then, take care, be safe, and I will see you guys on Wednesday. Later.